Hi everyone, this is a supplement to lecture 12 on how to solve linear systems. And in this video I'm going to show you how to use the Python's built-in tools, I guess through the Numpy library, actually not built in, but through the Numpy library to solve linear systems. So let's go ahead and get started. There's just two little parts to this. First we're going to talk about some matrix operations, and then I'm going to scroll down here and talk about solutions to linear equations. So we talked about matrix and other kinds of array operations using loops and arrays, and now we're going to sort of do the cheat and do the easy way and look at what's built in with Python. And we did some of the other stuff with loops and arrays in previous video. You can go check it out if you need to review those things. And we did that in part to sort of see what's happening under the hood here, but also in part to help us practice our loops and arrays. So now we're going on to the easier way. So suppose I'm just going to review these few functions here: how to add and subtract arrays, how to multiply arrays by scalar, how to do dot products, how to do transpose, how to do norm, and then we'll really quickly look at an inverse function. Okay, so suppose, and by the way, there's this link here you can follow. I'll put the link in the description of the video for more information about the Numpy and SciPy functions for linear algebra. Okay, so I'm going to start out here, import Numpy, and import these different matrices. So I've got the A matrix, the B matrix, a scalar S, and then an array B. And notice that if I have matrices, if I want to add them, I can simply use the addition operator, and that will do element-wise addition and subtraction. So if I have A and B, if I do A plus B, what I get is each element is added together. So here in A I have -2, in B I have 3, so finally in A plus B I have 1. In A I have 4, here I have in this element, in the 0, 1 element, I have a -4, and that is up to 0, okay, etc., etc. The same thing happens if I do A minus B, I get element-wise subtraction. So then I have -2 minus 3 gives -5, 4 minus a -4 gives me a +8, okay? So similarly, you can do scalar multiplication, so I can multiply A by just a single number S. S in this case was 4, so here I multiply A, if you remember up here, here's A, I have -2 times 4 gives me -8, 4 times 4 is 16, so the scalar goes through and multiplies every element. Okay, so those are things you probably already encountered before. We're just throwing them out there maybe as a reminder. Okay, so how do you do matrix multiplication? Use the np.dot function. So if I have A and B, if I want to do matrix multiplication, I can use np.dot, dot, and of course to use np I need to have imported Numpy as np up at the top here. np.dot, and I do A, comma B, and that's going to do a dot product. And remember, the dot product is, the 2 times 3, and then 4 times 7 summed together. So -2 times 3 is -6, 4 times 7 is 28, 28 minus 6 is 22. Okay, so it goes through and does that for you. I can also do a matrix vector product. So I can do numpy.dot A, comma little b, and now that will do the matrix vector multiplication here. And as I said before, in the past we've done this with loops. Sort of practice, it's a good practice for doing loops, but now we've got this easy function for doing the dot product. All right, suppose that we want to look even further at something like a norm. So a norm is basically in a vector, at least it's a way of getting an estimate of the magnitude of that vector. So think the distance formula of a vector. So if I have 2 points and I know the coordinates between those 2 points, and I want to know the distance, I'm going to take a norm. And what I'm going to do is take that length of that vector. It's going to have these different coordinates, and I'm going to take each of those each of the values, say x is 2 and y is 7. I'm going to take each of those components and square them. So 4 and 49, that would add up to 51. Okay, and then I'm going to take the square root of the sum. All right, and so that's what a vector norm is, and a matrix norm is very similar. It's also a way of telling a magnitude of a matrix. There's different kinds of norms, and I believe that the norm here in in Python is using the to-norm, which is the same thing. It takes a square and it sums all the elements up and takes a square root. So let's just check that out. So if I take a here, do np.dot, and here this one is inside the linear algebra package within inside Numpy. So Numpy has a little linear algebra package, so it's called linalg, or L-I-N-A-L-G, and you have to use np.linalg.norm of a, and notice that it returns back a number. So how could we figure out what that's really doing? Well, we would want to take each of these guys, -2 squared plus 4 squared plus 5 squared plus -1 squared. Oops, forgot the squared on the last. So that gives me 46. And if I take the square root of 46, that gives me exactly 6.78. Okay, so that's what the norm is doing there. And of course, I can also take the norm of a vector. So if I do np.linalg.norm, and I want to do it of little b, that will also work. And notice there, that's just 1 plus 9, the square root of that, or the square root of 10, okay, which is 2.16, right? So that's the norm function. And finally, for the transpose function, if I have this matrix A and I want to swap the rows and the columns, I do a dot t, and that gives me a transpose. So now the 4 comes down here and the 5 goes up there. The diagonal stays the same in a transpose function. All right, so that's it for part A here on basic matrix operations. So how do we go ahead and solve a linear system? There's 2 ways that we can solve a linear system. So, and remember, a linear system is some matrix A times an unknown vector x equals a vector b. Now there's 2 ways to go about doing that. One is a call to np.linalg.solve. So again, you're using the linear algebra submodule inside Numpy. And so to do that, you call np.linalg.solve of the matrix, comma b. And notice that it comes up with a nice little arguments down here, so you don't have to look them up. So you do a comma b. All right, and when you do that, it finds your value x. You can of course set this to be returned and assigned to the value of x if you want, and then when you look at x, it has that value. All right, so that's the easiest way. I recommend you do that way. But if you need an explicit inverse, you can also use an inverse function. So if instead of solving directly for x, I want to know what the inverse of a is, I can do a inverse is np.linalg.inverse, inv of a. Okay, and then a inverse now is a matrix, an inverse matrix, which if you recall, if I have ax equals b, the inverse is b is equal to a inverse times x. Or excuse me, x is equal to the a inverse times b, okay, where there's a dot product here. And this should have a dot there. Okay, that's just a silly little thing to do, right? But we can actually test that. We solve for x, right? So we can do np.dot a inverse b, all right? And it should also give us x, and lo and behold, it does. So if you want to solve for x, you can solve for it 2 ways. You can first you can just do the linear algebra.solve, or you can do linalg.inverse, store the inverse matrix, and then do a dot product with that times b to get out x. All right, either one is fine. The advantage to using the solve is that you do it in 1 step, and it's also numerically a little bit better because you don't have to store that inverse matrix. But suppose that you wanted to solve many different systems. You could, you could keep that inverse, and then you could solve it with one right-hand side vector b, and then you could do something later, and then you could again solve it another time later. Generally speaking, if you want to do something multiple times, storing the inverse is actually even still not optimal. There's another algorithm called LU decomposition that you'd want to look up and check out. We're not going to cover that in this video or in the class, but that is something you can check out. Okay, so here's a couple examples down here doing exactly what I showed you. Finding the solution x and finding b, and then checking the answer back again. So note that you can always check the answer. So if I solve for x, then I can do np.a comma x, and that should equal b. So this is really convenient, and a thing that you can calculate every time in these linear systems to make sure that you have the right answer is you take a dot x and subtract b, and you should get a matrix of zeros. And then if you take the norm of that, so if I take linalg.norm of that entire quantity, then that number should be really, really close to 0. And there I am, pretty close to machine precision, around 10 to the minus 16 for doubles. Okay, and so this value here, the norm of the difference between the right-hand side and the left-hand side, is called a residual, right? So it's the amount left over, it's the residual when I've already tried to do this, okay? So again, you can calculate that linear system here both ways, whether you do it the inverse way or the other way. So why don't you pause the video real quick and see if you can't do this practice on the linear system here. So see if you can't sum a and b, and then see if you can solve this system here where a plus b dot x is c dot b. See if you can figure it out all by yourself. I'm going to go ahead and work it out right after I finish talking here, but pause the video, see if you can do it by yourself and see what happens. Okay, so now I'm going to solve this system a plus b. I'm going to plug it in here so I don't have to just type it in the console. So let's see what happens. So the first thing here is you need to set up np.array. Okay, you need to set up these matrices. So this is a 5 by 5 system, so it's going to be a little bit of work to do. I'm going to need 5 of these guys in here. Almost 1/5. Okay, A, B, oh, forgot this one should be C, right there, and little b. Okay, now I want to solve this. A plus b dot x. Okay, so now that's all typed in. Now I want to solve this system. A plus b dot x is equal to c dot b. Well, what's going on here? This looks just like ax equals b, except I have to calculate this, and then I have to calculate this to a new right-hand side. So I'm going to call a prime equal to a plus b, right? Because I have a plus b right there, and that's going to be my new a. And I'm going to call b prime equal to what? C dot b. Well, how do I do that? I do np.dot c comma b. Boom. Okay. Now I have a prime dot x is equal to b prime. So now I have a prime dot x is equal to b prime. All right. So how do I solve that? Well, I use my old solver. So I do x is equal to np.linalg.solve of a prime comma b prime. All right, and how do I check my answer? I want to check that this is true. So I do a prime dot x minus c dot b. So I do a prime numpy dot a prime dot x minus b prime. And I'm going to take the norm of that. Then I'll call that the residual. And then I'll print out x, and I'll print out the residual. And voila, this prints out a bunch of stuff from up here with these solutions. But if I look down here, if I care about at the end, x and the answer, maybe I'll even put that in, x equals x, and then the residual equals the residual, and then I give a couple of lines. Ooh. Like that, put out an extra couple of lines, and there you go. I solved for x, and the residual is a very small number, 10 to the minus 15th, and I'm done. Okay, so that's using Numpy linear algebra tools to solve linear equations in Python.